The following is an encore presentation of Everything Everywhere Daily. You've seen it in your science classroom, and there was probably a copy of it on the inside cover of your chemistry book. Maybe if you're a real nerd, you might even have your own personal copy. Yet its very creation was a revolutionary breakthrough that helped scientists and generations of students understand the very things that make up our world. Learn more about the periodic table of elements and how it helped explain our natural world on this episode of Everything Everywhere Daily. I'd like to introduce you to Story Pirates, the award-winning podcast where talented comedians and songwriters transform kids' stories into laugh-out-loud sketch comedy and catchy original songs. Featuring crazy, wacky, clever tales straight from kids' imaginations, this show is a must-listen for children and grown-ups alike. Why will you love Story Pirates? First, all the stories are by kids for kids. The performers are from such notable shows as SNL, Sesame Street, and The Tonight Show. You'll hear guest stars like Lin-Manuel Miranda, Kristen Bell, and Steph Curry. And it's been recognized by the Webby Awards and downloaded over 85 million times. Ready to laugh, sing, and be inspired? Join the millions of listeners tuning in to Story Pirates. Listen to Story Pirates wherever you get your podcasts. The very first elements were discovered by early humans. The very first ones were all metals. Copper, lead, iron, silver, gold were some of the very first elements that humans recognized. They had no clue what an element was or an atom, but they knew it was a thing, and they knew that one thing like copper was different from another thing like iron. By the time the end of the 18th century rolled around, America was a newly independent country, and there were a little over 24 known elements at the time. In 1789, a French chemist by the name of Antoine Lavoisier made the first systematic attempt at trying to list all of the known elements. He came up with a list of 33 elements and grouped them by known attributes. He primarily divided them into metals and nonmetals. Unfortunately, many of his elements weren't really elements. He included things like light and heat, which weren't even physical things. However, he did get one thing pretty much right. He defined an element as something which could not be broken down any further. Today, we call them atoms. As the 19th century began and chemistry became more sophisticated and analytical, there was a rush of new elemental discoveries. Dozens of new elements, usually rare ones, were discovered in the first half of the 19th century. In 1829, German chemist Johann Wolfgang Dobereiner got a little closer. He noticed that many of the elements that displayed similar properties could be grouped into threes, and that the atomic weights of the elements were all next to each other. Over the next few decades, as more elements were discovered, chemists noticed that there was a pattern with how elements bonded to each other. For example, carbon could bond to 4 hydrogen atoms, or it could bond to 2 oxygen atoms. However, all the attempts to try to organize all of the known elements didn't work. It seemed to make sense in bits and pieces, but when you tried to put it all together, nothing seemed to make sense. In 1860, a conference was held in Germany on the subject of atomic weights. They determined that hydrogen had an atomic weight of 1, and that every other element would be measured in comparison to hydrogen. In 1862, a French geologist named Alexandre-Émile Bière de Champcauchois came really close when he noticed that there was a periodicity in the elements. This was a huge step forward in understanding how everything fit together, but it wasn't quite there yet. He actually proposed organizing them in the form of a helix or a screw. The 1860s saw several other attempts at organizing the elements, and each attempt brought something new to the table which helped describe the elements in relationship to each other. There was one problem, however, that no one had figured out. The big breakthrough in the organization of the elements came from a Russian chemist named Dmitry Mendeleev. In 1869, he published his table, in which he used rows and columns to organize the elements by atomic weight. He would start a new row when attributes started to repeat. The breakthrough element of his chart, and the thing that no one else had really done until this point, was that he left empty spaces where there were undiscovered elements. Everyone else just put all the known elements together, and that was why everything didn't fit. Mendeleev just let the atomic weights speak for themselves, and if there wasn't a known element that fit, he just assumed that it would be discovered later. By leaving spaces empty, he also guessed at what the general property of the new element in that spot would be. He was also willing to occasionally ignore the order of atomic weights when it made sense and occasionally switched elements around. His first table in 1869 wasn't perfect. He produced another table in 1871 which had more spaces for undiscovered elements. There was also one big unresolved problem. There was a huge gap in atomic weights between the elements cerium and tantalum that he couldn't resolve. At first, no one really gave his table much attention. Then, a huge discovery in 1911 really set the periodic table on firm ground. New England physicist Ernest Rutherford discovered the nucleus of the atom. After that, it was suggested that the chart follow the atomic number of the atom, which is the number of protons in the nucleus. It turned out the table was almost already a perfect fit. Based on this new understanding of the periodic table, English physicist Henry Moseley predicted in 1913 that there were still 3 elements to be discovered between aluminum and gold. His prediction was 100% correct. The last natural element discovered was francium, which was discovered in 1939. That big gap between cerium and tantalum was finally resolved by Glenn Seaborg in 1942, who identified the rare earth elements which are usually separated from the rest of the chart at the bottom. They are also known as the lanthanines and actinines. One of the interesting implications of the periodic table is that the last natural element is uranium, with an atomic number of 92. However, there are a bunch of empty spaces beyond the number 92. Unlike the missing elements lower on the chart, these can't be found in nature, so scientists have been working over the decades to make them themselves. The elements closest to uranium can be created via nuclear reactions. However, the farther out you go, the only way to make them is via smashing together other large atoms. As of 2009, researchers have created all of the elements to fill up the table. The last artificial element to be created was element 117, which is called tennessine. The last element on the periodic table is element 118 called oganesson, and it falls in the same column as the noble gases. All of these artificial elements have extremely short half-lives and often don't exist more than a tiny fraction of a second. It isn't known if there are stable elements further out, or if there might be stable versions of the atoms that they've already created. So, how do you read the periodic table? Starting in the upper left with hydrogen, it goes horizontal by atomic number. Hydrogen is 1, helium is 2, lithium is 3, etc. As I mentioned before, the atomic number is the number of protons in the nucleus, and that's what determines what an element is. Each row is called a period. Each period corresponds to the number of electron shells the element has. The first shell has 2 electrons in the shell, so there are 2 elements in the first row. The second and third shells have 8 electrons, so there are 8 elements in the second and third row. The rare earth elements at the bottom are usually displayed separately, but they do fit on the table. However, if you printed the table with them in their proper place, it would be really wide, so it usually isn't presented in that fashion. Each column is known as a group. The group reflects the number of electrons in the upper electron shell. The first column is known as the alkali metals. All of these metals have 1 electron available, and everything in that group is extremely reactive. This includes lithium, sodium, and potassium. If you haven't seen it, go look up a video to see what happens to these elements in their pure metallic form when they're placed in water. There are many videos online that show this. They are all explosive, and they get more explosive the further down the group you go. In the last group are the noble or inert gases. They rarely react with anything because their electron shells are full. They include helium, neon, argon, xenon, and radon. Metals tend to be on the left side and in the middle. The periodic table is really an amazing thing. It so neatly and cleanly encapsulates how all the elements which make up the world relate to each other. It isn't just a handy educational aid, but it also should be considered an actual thing of beauty. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Benji Long and Cameron Kieffer. I want to give a big shout out to everyone who supports the show over on Patreon, including the show's producers. Your support helps me put out a show every single day. And also, Patreon is currently the only place where Everything Everywhere Daily merchandise is available to the top tier of supporters. If you'd like to talk to other listeners of the show and members of the Completionist Club, you can join the Everything Everywhere Daily Facebook group or Discord server. Links to everything are in the show notes.